Welcome to The Explainer. We're going to talk about something pretty wild today. A piece of tech that was originally designed just to make your video games look amazing, but somehow it accidentally became a key to solving some of humanity's biggest problems.
So, what if the answer to some of our biggest questions was hiding right there in your gaming PC? That's not science fiction. It's the incredible true story of the GPU, the graphics card. We're talking about how these things became these accidental supercomputers, totally changing the game for science, medicine, and of course, AI.
All right, so let's set the stage. We're going back to the late 90s. Gamers wanted more. They wanted more realism, more polygons, more everything. And that massive demand, it drove this insane race to build more and more powerful graphics processors. But while all that was happening, a few really sharp programmers looked at all that horsepower and thought, wait a minute.
They had this aha moment. They realized all that raw power for drawing triangles and pixels could be hijacked for anything. For general-purpose computing. You could use it to crunch numbers for scientific simulations or search through enormous amounts of data, and that's how we got the term GPU. And let me tell you, this wasn't just a small step. It was a total game changer. It's literally the foundation of the AI boom we're living through right now.
But, it wasn't easy. Not at all. In the early days, you basically had to trick the GPU. Programmers had to be these digital contortionists, twisting their science problems so they looked like graphics problems. They were literally thinking in terms of colors and pixels just to do math. It was a huge headache. That is, until platforms like NVIDIA's CUDA came along. CUDA was revolutionary because it created a direct line, a way for programmers to talk to the GPU without all that weird translation.
Okay, so we've established that GPUs are powerful, but how are they different from a CPU, the main processor in your computer? It all boils down to how they're built, and they have two completely different approaches to work.
I love this analogy. Think of your CPU as a master chef, right? It's got maybe a handful of very sophisticated cores. It's a genius at tackling complex jobs one after another, in sequence. But a GPU, that's a completely different beast. It's like a gigantic assembly line with thousands of workers. Each worker isn't a master chef. They're really good at doing one simple, repetitive task. And the key is they all do it at the exact same time. That's the single instruction multiple data or SIMD architecture we're talking about. And that is the secret sauce for AI, which is all about massive parallel number crunching.
So let's see how this assembly line actually works in practice. Picture the foreman shouting out a single command to everyone. Hey, if the number you're holding is positive, add 1 to it. So all the workers with positive numbers get busy. But here's the catch. What's everyone else doing? Nothing. They're just sitting there, idle. Then the foreman yells the second part. Okay, everyone else, subtract 2. Now the first group is idle and the second group starts working. You can see the power here, but you can also see the problem, right? You've got half your workforce sitting on their hands at any given moment. That's not super efficient.
So how do you fix that? Well, the solution is actually pretty clever. Modern GPUs don't just have one big assembly line. They have multiple assembly lines, each with its own manager, what we call a streaming multiprocessor, or SM. So now the foreman can send the if group to one SM and the else group to another SM, and they can both work at the exact same time. No more waiting around. This one little change makes a huge difference in efficiency.
Okay, so you've got this massive army of thousands, even millions, of little digital workers. How on earth do you keep them all organized? How do you prevent total chaos? Well, you need a brilliant command and control system, and for GPUs, that system is CUDA.
CUDA sets up this really elegant chain of command. At the bottom, you have the individual worker, which is called a thread. You group a bunch of threads together into a team, and that team is called a block. And then the entire collection of all the teams working on the job, that's called the grid. It's a simple, powerful way to make sure every single worker knows exactly what its job is.
And here's the really beautiful part. A programmer can launch this entire army with just a single simple command. They write one line of code to call what's called a kernel. That's just a fancy name for the job they want done. And in that one line, they say, I need this many teams with this many workers in each team. And boom, the whole army gets to work. It's an incredibly efficient way to manage all that complexity.
But there's a catch. Anytime you have thousands of things happening all at once, you run into a fundamental classic problem, a coordination problem. And if you don't solve it, you don't just get a slow answer, you get a completely, catastrophically wrong answer.
So let's set up the problem. Imagine we're trying to add up a bazillion numbers. We've given a small chunk of that job to each of our thousands of threads. They've all done their little bit of math. Now, all they need to do is add their small result into one single, shared final total.
What happens next?
Well, imagine 1,000 people all trying to update a single number on a single whiteboard at the exact same time. It's chaos. 2 people might run up, read the number, go back to their desks to add their piece, and then run back to write the new total. But whoever writes their number last just erased the other person's work. This nightmare scenario has a name in computer science. It's called a race condition.
Let's walk through exactly how this goes wrong. Okay, so the total on the board is 100. Thread A comes along and reads 100. At the very same instant, thread B also reads 100. Now, thread A goes off, adds its value, let's say 5, and writes 105 on the board. But wait, thread B still thinks the number is 100. It adds its value, let's say 10, and writes 110 on the board. See what just happened? Thread A's work is just gone. Poof. The right answer should be 115, but we ended up with 110. Data lost, calculation wrong.
So, the brute force solution is pretty obvious, right? You just make everyone stand in line. And there's a command for that. It's called atomic add. It basically puts a lock on the whiteboard. Only one thread can read, write, and update at a time. It works, for sure. You get the correct answer, but it's painfully slow. You've just taken your parallel supercomputer and forced it to work in a single file line. It completely defeats the purpose. So clearly, that's not the way. The single file line kills our performance. We need a smarter way. Instead of making everyone work alone, we need to teach them how to collaborate, how to use teamwork. And here's how that teamwork looks. Instead of every single one of those thousands of threads storming the main whiteboard, we get them to work in small squads. These are teams of 32 threads called warps. The first thing they do is figure out a team's subtotal. And they can share their numbers with each other super fast using a couple of tricks. One is a special high-speed shared memory that's just for their team. The other is an even cleverer trick called a warp shuffle, which lets threads literally grab the answer right from their teammates' fastest possible memory. It's like whispering the answer to the person next to you instead of shouting it across the room.
Now, once the whole team of 32 has its subtotal, only one of them, the team leader, has to go up to the main whiteboard. So instead of thousands of threads creating a traffic jam, you only have a few dozen team leaders lining up. The bottleneck is basically gone.
And the results? Well, they speak for themselves. Look at this. The original, safe but slow atomic add method took over 3 milliseconds. That might sound fast, but in computing, that's an eternity. Now look at the teamwork methods. The warp shuffle or using shared memory. We're talking about 0.14, 0.15 milliseconds. That's not just a little faster. That is 20 times faster. It's a night and day difference.
And that really gets to the heart of it, doesn't it? It's not just about having a fast processor. The real magic, the real leap forward in computing power is figuring out how to get millions of individual parts to work together, effectively.
So this whole revolution started kind of by accident, just to make video games look cooler. And now, GPGPU is at the core of everything, from discovering new medicines to modeling climate change to, of course, the AI that's changing our world. The story is definitely not over, which makes you wonder, right? If this is what we've done so far, what else can we teach these digital armies to do?
Thanks for joining us for this explainer.